Now, sorry that I have to pull you to the Zoom lecture on the Saturday afternoon because we have missed 2 hours of lecture on Thursday, and the midterm should be coming on the 19th of October. Topics to be covered would be up to chapter 11. So it would be about up to the angular momentum. We are still at unit number 10, rotation of a rigid object about a fixed axis. So we are still some distance from it. And the concepts, I should say, they are not very straightforward for many of the students. So I would be anxious to finish the lecture as quickly as I could, and at the same time try to make sure that the lectures are delivered clearly to most of you, if not all. And I would try to bring out a couple of tutorial questions, and we try to go through them during the lesson. So at here, let us recap what we have seen in the last few lessons. We have, of course, started on the topic of the rotational motion, and we are kind of following the logic of discussing the motion in the linear case. We start by talking about the parameters that we frequently use in the rotational motion. They are the angular displacement, angular velocities, and angular accelerations. So these are the fundamental parameters that will be used to describe the rotational motion of an object, a rigid object, about a certain fixed axis. Rigid object is necessary because if it is not rigid, motion along the radial direction can occur, and that would be very complicated. And we fix our axis so that we are not complicating the behavior. In fact, later we will see an axis that could also be moving as well, and that would be the combined motion of linear and rotational motions. That is the case of rolling. We will see it in the end of chapter number 10. So this set of lecture notes at the end, we will talk about the rolling motion. So at the beginning, we talk about the these parameters, and we talk about the kinematic equations. It is very important to note that many of these rotational kinematics equations, you could find the similarity with the case of linear motion. Of course, they are fundamentally different. They are fundamentally different in the sense that one is concerned with the motion along a straight line, that is the linear motion, and one is concerned with the rotation about a fixed axis. But you could compare the equation forms. They look very similar. In the case of an object moving in a linear fashion, all the particles in the object, they move with the same displacement, acceleration, and velocities. Implicitly, we are assuming that the object is rigid as well. In the case of a rotational motion, all the particles are rotating about a fixed axis with the same angular displacement, angular velocities, and angular acceleration. That is for the case of a rigid body rotation, rigid object rotation. And in the, let me see, in the lesson on Tuesday, we started by talking about rotational kinetic energy. Here, we are not talking about a rigid object to start with. We are not talking about a whole rigid body to start with. We are talking about individual particles. Considering that a rigid object is actually a collection of many particles. So each of the particle would have a kinetic energy. And the kinetic energy can be considered in the linear motion way because of the rotation about a fixed axis. Every particle, when it is moving in the rotational motion, there is a corresponding linear velocity and linear acceleration. And that is proportional to the distance from the radius, proportional to the radius of motion. So we could treat every single particle on the rotating object to be performing a linear motion. For linear motion, the kinetic energy is 1/2 mv squared, something we know quite well. Of course, we have a collection of particles on a rotating object, so we just add them up together. And through the process, we found that there is yet once again similarity between the equation forms. For the linear motion, kinetic energy is 1/2 mv squared. Of course, you could have a collection of particles in the object moving in a linear motion. So you add them up together, and at the end, you just sum up all the masses. Velocities in the linear motion is the same for all the particles in the object. That is implicitly assumed. In the case of a rotational motion, we could do it in a similar way. Now, 1/2 is common term, so we could take it out of the summation sign. We could take it out of the sum of all the terms. Omega squared, it is also the same for a rigid body rotating about a fixed axis. What is not fixed would be m and r. So here we have an equation form that looks very much like the linear kinetic energy. 1/2 times the inertia times the velocity squared. Here, 1/2 times some kind of inertia times omega squared. And this some kind of inertia, it is for the rotational motion. This inertia is related to the mass of each particle and the location of each particle from the axis of rotation. So this term, summation, the sum of mr squared for each particle, we call it the moment of inertia. And this is the inertia of a rotating object about a fixed axis. Now, if you have only one particle rotating about a fixed axis, that is very easy. That is just the m times r squared for that particle. But if you have a multiple of particles, that would be quite complicated. So in the lesson on Tuesday, we look at the case where you have 4 masses on a cross, and we are rotating this object about different axes. So in the first case, we rotated about the axis through the small masses m. And in the second case, we rotated about an axis perpendicular to the plane of the cross. You can see that the moment of inertia would be different for the 2 cases. So unlike the case of a linear motion, moment of inertia, it is not constant. For linear motion, the mass of an object is a constant. But for rotational motion, moment of inertia, it is not a constant. It depends on where you put the axis of rotation. So here you see the difference of the axis of rotation, and this would give rise to different values of I. And here is the definition. You have multiple particles. Let me see if I could show it. Oh, it doesn't matter. Okay, here. So if you have a multiple particles, the moment of inertia is defined in this way. And the unit of moment of inertia is kg times meter squared. Very importantly, unlike the case of a linear motion, where the inertia, which is mass, it is independent of the choice of axis, but the moment of inertia, it depends on the choice of the rotation axis. So that is something we have to be very careful about. And in the case where you have a continuous object, then the moment of inertia could be calculated by integration. Once again, these equations are for reference, just to show you how the concept of integration comes into effect. Initially, this is the definition, mi times ri squared. You have many particles. I correspond to a label for a particular particle. So you could have I running from running from 1 up to infinity. You have an infinite number of particles. That is up to you. And each of them have a corresponding mass, and they have a particular distance away from the axis of rotation. So the idea is mi times ri squared. And if the particles are infinite in numbers, mass of them tends to 0. So this one, it is fitting into the form of integration. So if you turn it into the integration equation, this would be the writing. You are turning the sum into an integration, r squared times dm. dm corresponds to an infinitely small mass. We could view it in this way. Of course, we are not asking for deviation by integration. But in the next few slides, we will show you a couple of examples how they could be derived actually. The trick in many of the cases is you try to change the mass, the small mass, to have some relation with the radius from the axis of rotation. So that is the usual idea of calculating the moment of inertia. So for example, at here, you have the case of a rod rotating about its center. So we are rotating the rod about the y-axis, and we are putting the center of mass to coincide with the y-axis. So we have many particles on the rod, of course, and these particles runs from the length of L, well, runs from the locations x equals to minus L over 2 to positive L over 2. Just to make sure that this is a rod of length L. So it runs from minus L over 2 to plus L over 2. And each of them has a certain length dx. That is for integration purpose. So for this particular length dx, it would have a corresponding mass that is given by the equation at here. Lambda corresponds to the mass per unit length. This is a rod with a uniform density. So for a certain length of the rod, it has a corresponding mass, and that they are proportional to one another. So that is why we could write down the equation like that. Lambda is equal to m divided by L for a rod with uniform density. And the cross-section would be uniform as well. So you are just changing the location from the center of rotation. So here we put the dm into the integration, and what you will find is that r could be replaced by x dash, which is the distance from the axis of rotation. So the mass dm is m over l times dx. So here you have an equation that could be integrated. And at the end, we find the value 1 over 12 ml squared. And that is for rotation about its center of mass. What if you rotate the rod about its end? So you see there are two equations for I, two equations for moment of inertia. One is for rotation about its center of mass, 1 over 12 ml squared. The other one is for rotation about its end. So the integration is slightly different. As you could see, the difference is at the starting and the ending positions. In the first case, it is from L minus L over 2 to plus L over 2. In the second case, you start from L equals to 0 and then ends at the length of the rod. So it's from 0 to L. The integration will give you a different value, and that is equal to 1/3 ml squared. So the lesson to be learned here is, well, I'm not telling you once again to do the integration. I am saying that the moment of inertia could be different depending on the choice of the axis of rotation. So you move the axis of rotation from here to here. Moment of inertia changes from ml squared over 12 to ml squared over 3. That is something you have to be very careful about. And this is another case of calculating the moment of inertia. Once again, you are considering particles that are at a certain distance from the axis of rotation. Here, we explained it in the last lesson. We are considering cylinders of material. So each of the cylinder has a radius r. So all the particles are equal distance from the axis of rotation. Z-axis is the axis of rotation in this case. All the particles on the cylinder, the highlighted blue one, they are at distance r from the axis. So this cylinder would have a volume, the highlighted cylinder I'm talking about, the highlighted cylinder has a volume that is equal to the cross-sectional area times the length, 2 pi r, circumference times the thickness of the cylinder, dr, times L. And the mass of this highlighted cylinder, it is equal to density times dV. So you get this equation. The moment of inertia is integration r squared times dm. You put the dm into the equation. So you are starting the distance r from 0 up to capital letter R. So 0 to capital letter R. And all the terms inside are ready to be integrated. So at the end, you would get something like this. By replacing the term of density, which is equal to the mass divided by volume of the cylinder, volume of the whole rod, actually. V is the volume of the whole rod. M divided by pi r squared L. So you would get the moment of inertia for this rod rotating about its long axis. It is equal to 1/2 mr squared. Now, think about it. You are changing the axis of rotation once again. In the previous case, the axis of rotation, it is along the y-axis. You may have it passing through the center of mass or at the end of the rod. Now, the axis of rotation could be considered to be along the x-axis in the page 26. You just rotate the whole thing by 90 degrees. You rotate the axis of rotation by 90 degrees. So here, the rotation is about the rod. dA is the shaded area as shown in this slide. So 2 pi r is equal to circumference times dr, which is the thickness of this highlighted shell, cylinder. So you see that once again, the moment of inertia changes. So the lesson, again, choice of axis is very important to decide the moment of inertia. And I mentioned in the last lesson, we are not asking you to calculate or to do the integration. We are not asking the students to do the integration and find out the moment of inertia for a continuous object. But we have some standard equations for various scenarios. Say at here, you have, let me try to magnify a bit in here. So you have a moment of inertia about is a long axis for the cylinder. So he's a 1/2 mr squared. If the cylinder is not a solid one, but actually a hollow tube, and the tube has a very thin thickness, the thickness is very small, then you could consider that all the particles are at the same distance r from the axis of rotation. In that case, the total moment of inertia for this hollow shell, it will be equal to mr squared. Or for the case of a solid cylinder, rotating about the long axis, it will be 1/2 mr squared. So there is a difference between the cases. On the other hand, you would have the, say, rectangular plates or rods rotating about different axes. They would have different moment of inertia. For rotation of solid sphere or just a thin shell of a sphere, they would have the different moment of inertia. But both of them would have the axis passing through the center of mass. So there is a very tiny point which you have to be careful about in this slide. And that is all of the terms are labeled with, all of the moment of inertia, they are labeled with ICM, meaning that it is the moment of inertia passing through the center of mass, except this one. Even the last two, they are talking about the moment of inertia passing through the center of mass. So the axis would be passing through the center of mass, except this one. Here, the center of mass, of course, for a uniform rod, it would be right at the center of the rod. But now the axis of rotation is at the end of the rod, so it is not passing through the center of mass. So be very careful in the notation at here. So you may wonder, well, every time it seems that we have to calculate the moment of inertia about different axes, and that would be quite tedious task. And in fact, it is. It is a very tedious task if you are trying to do the calculations for the moment of inertia for all different situations. But it well, some of you ask why there is a difference between a shell and a solid. It is related to the distribution of the mass. In the case of a shell, you have all the masses. You have all the masses. That is at the furthest possible distance from the center of rotation. And here, for the solid, you have quite a lot of the mass that is much closer than the radius of the sphere. So this would give rise to a difference to the moment of inertia. Of course, the final answer has to be calculated. But we could simply argue that due to the distribution of the mass, this would give rise to the difference in the moment of inertia. Now, coming back to what I've just talked about, if you have the axis of rotation that is changing from one place to the other, like in the case of a rod, like here, and here, this rod, if we are moving the axis of rotation from the center of mass location to the end, would there be a simpler method to do the calculation? The answer is yes, as long as we have these two axes of rotation that are parallel to one another. If the two axes of rotation are parallel to one another, and we could relate the moment of inertia that passes through the center of mass to the moment of inertia passing through any other location by a simple equation. And that is what we call the parallel axis theorem. The idea, once again, is this. You have, say, the rod, for example, just to make it easier, you have a rod. Originally, you have the moment of inertia for passing through the center of mass. So if you take a look at the video screen that I'm showing, let me see. So at here, you have the moment of inertia for passing through the center of mass. And if you move the axis of rotation parallel to the initial axis, so they are parallel to one another, the distance of movement, let us call it d. So you do not even need to necessarily put it at the end. You could put it somewhere in the middle of the rod as well. As long as it is parallel to the axis of rotation of the original one, and the original one passes through the center of mass, the new moment of inertia is related to the moment of inertia passing through the center of mass, I mu. It is given by the equation ICM plus md squared. D is the distance between the two axes of rotation, and m is the mass of the whole object. M is the mass of the whole object. This is the case of the rod. You could have the case of a sphere. Originally, you have a sphere, and the moment of inertia passing through the center of mass is this one. Now, you may move the axis of rotation such that it is now actually touching. It is touching the surface of the sphere. So if the radius of the sphere is r, then I nu, in this case, it is equal to ICM plus m r squared. This is the parallel axis theorem as in your page 28 of the lecture notes. Important word is the parallel axis. The original axis and the new axis, they are parallel to one another. And the distance between them is given by d. So I new is equal to ICM plus MD square. Of course, here the d is equal to r, so I write mr square. The deviation for this parallel axis theorem, it could be found in your lecture notes. So I just go through it very, very briefly. Now, here it is the deviation. The idea is like this. The idea is like this. You will have a plate. Well, just to make it simple, a plate that is rotating about the axis, z-axis. Z-axis is the axis of rotation right now. The moment of inertia for this object rotating about the z-axis is I. Moment of inertia for the same object rotating about its center of mass is ICM. For any particle on this plate, as compared to the axis z, it is at a distance, or it is at a coordinate x and y. For any particle, dm, it is at a coordinate x and y from the origin. But as relative to the center of mass, the coordinate, on the other hand, would be x dash and y dash. So you could start to calculate the moment of inertia about the z-axis by the equation integrating r squared times dm. R squared, by Pythagoras theorem, it is x squared plus y squared, and then dm. So we could take out the terms. What is x? X is actually equal to xcm, the location of the center of mass from the origin, plus x dash, as you can see here. Similarly, y is y dash plus ycm. So this one could be expanded, so it becomes x dash square plus y dash square. Now this one, you could see that x dash and y dash are seen on the diagram. This would be the location of the particle from the center of mass. So x dash square plus y dash square, it becomes the moment of inertia about the center of, about the axis passing through the center of mass. This is the ICM. The second term, 2xcm times integrate x dash dm. This one is actually similar to what we've seen in defining the center of mass. You have all the particles evenly distributed about the center of mass. So x is the distance times dm, mass of the particle from the center of mass. So this would actually be 0 because the rotation or the this term about the center of mass has to be equal to 0. Otherwise, it is not the center of mass. It is the definition of the center of mass. Similarly, y dash times dm, it is equal to 0 as well, for it is the meaning of the center of mass. And the last term, x cm squared plus y cm squared, it is equal to the distance of between the axis of rotation and the axis passing through the center of mass. So the integration of this last term, because xcm is a constant, ycm is a constant, it can be taken out. And the integrating of dm, this one, it is just to sum up all the masses, and that is actually the whole mass of the object. So that is the large M. And at the end, you would get this equation, I equals to ICM plus MD squared. The important message, once again, it is the axis between the two cases must be parallel. The axes are parallel, and one of the axes must be passing through the center of mass. So that is the idea. With that, let us try to find out whether we are actually making sense of our previous calculations. You have this rod, and here the rod, it is having the axis of rotation about its end. How does the moment of inertia compare with the moment of inertia passing through the center of mass? So when it is passing through the center of mass, the moment of inertia, ICM, it is ml squared over 12. The axis is now moved by a distance of L divided by 2. So D is equal to L divided by 2. So new moment of inertia about its end, it is ICM plus MD squared. So this one, when you add them up, it is equal to 1/3 ml squared. So all the things seems to make sense in this situation. Okay. So at here, let us try to take a look at some tutorial questions, and they would be related to the calculation of moment of inertia. So for example, let us take a look at the question number 3. The diagram of question number 3 is shown in here. It's a bit difficult to show both at the same time. Let's try. Okay, the diagram of question number 3 is the middle one. Okay. So right now we are having 3 identical rods. Each of the rod would have a length of L and mass M, and they are welded into a 3-dimensional cross, if you like. The assembly is now rotating about an axis, passing through one of the ends of the rod. So the rotation is about this particular point at here, and we would like to determine the moment of inertia for the whole structure. In this particular case, let us try to make the things simple. Of course, we could always work out the moment of inertia by considering 3 separate rods. Each of them have a moment of inertia about this dashed line as the actual axis of rotation. But let us try to make the thing simple and apply the parallel axis theorem. We first consider the rotation about y-axis. We consider the rotation about the y-axis. So if you consider rotation about the y-axis, things are actually quite straightforward. If the axis of rotation is a y-axis, it is passing through the center of mass for all the rods. Moment of inertia for the rod along x direction, moment of inertia about y-axis, according to the equation in the lecture notes, ml squared over 12. Similarly, the rod along the z-axis, moment of inertia about the y-axis, ml squared over 12. What about the rod along the y-axis? Because it is lying along the same axis of rotation, it is a very thin rod. So all the particles at a 0 distance from the axis. So it is not contributing to the moment of inertia. So at the end, it is only the x-axis rod and the z-axis rod contributing to the moment of inertia about the rotation through the y-axis. So I try to show you the solution for easier visualizing. No worry, the solution eventually would be displayed also on the blackboard on the Learn at PolyU. So here I just give you a very quick look. Rotation in the line at here is for axis passing through the y-axis, so through the center of mass. About the for the rod along the x-axis, for the rod along the z-axis, they contribute to 1 ml squared over 12. For the rod along the y-axis, they contribute nothing. So moment of inertia, 1/6 ml squared. And then by parallel axis theorem, you are moving the axis of rotation by a distance of L/2 along the x-axis direction. The rod is thin. So all the particles are right on the axis. mr squared for all the particles is equal to 0. Remember the definition of I, it is equal to the sum of mr squared. If all the particles are right on the axis, that is the rod rotating about its long axis, and if the rod is very thin, R approaches 0, then moment of inertia will be 0. So if you are then moving the axis by L/2 by the parallel axis theorem, you would have ICM plus total mass 3m times d square L divided by 2 square. So that would be giving you the final answer of 11 over 12 ml square. So that is the idea of calculating the moment of inertia in this case. Okay. Now, I will take a break about 10 minutes. And after that, we would be looking in the topic of torque. I'll be looking into the topic of the torque, and that is the equivalent of the force in the linear motion. Okay. Okay. So I would be addressing the question on the chat room, and well, I may take a break for 5 minutes, and then afterwards I would answer the questions on the chat room. Okay. Okay, now let us come back to the class. Just before the break, we spent some time talking about the calculation of the moment of inertia. And from this point onwards, I will be talking about another concept that has an analogy with the force in linear motion, and that is the torque. In the case of a force in the linear motion, we know that it is related to the change of the acceleration, but it is a reason for causing the acceleration of the objects. And we will see later that a similar effect could occur when you apply a torque to a rotating object. So let us try to figure out what the torque is at the beginning. The idea of the torque, it is for changing the rotational motion of the object. You could always think of it in this way. In the case of the force, you are changing the linear motion of the object by causing it to accelerate. In the case of the torque, you are changing the motion of a rotating object by causing it to accelerate in the rotational sense. Of course, acceleration could be positive or negative. So you could be increasing the angular speed or decreasing the angular speed. But in any case, you are changing from a original type of motion, original pattern of motion into another. Say in the diagram shown here, you have a spanner. And in order, at the beginning, you try to tighten the nut in the diagram. So the nut is at the center. So in order to tighten it, you need to accelerate, rotationally accelerate the nut. Otherwise, it would just keep stationary without any angular displacement. So in order to have angular displacement, you need to accelerate it. So by our common sense, we know that we need to turn the spanner by applying a force at the end of the spanner. Why at the end of the spanner? Because if you try to apply the force in the middle, you will find that it is much harder. But if you apply the force close to the end, it would be much, much easier. So for the same turning motion, or same angular acceleration, if you like, if you have the distance of between the force and the axis of rotation that is longer, the turning effect would be greater. So that is why the turning effect is related to the distance between the force and the axis of rotation. So that is the R. At the same time, if you apply a greater force, you would also be able to imagine that a larger force should have a stronger turning effect. These are something we commonly encounter. These are effects that we commonly encounter in our daily lives. Yet, when we talk about a force, we must know that it is a vector. So the direction of the force matters a lot in your calculation of the turning effect. Say, if you apply the force along the length of the spanner, it is not helping to turn the nut. If you apply the force along the spanner, at the most, you are pushing the spanner very hard on the nut or just trying to take the spanner away from the nut. It will not cause it to turn at all. In order to have some turning effect, the best strategy is to apply the force perpendicular to the length of the spanner. So we have this concept that the turning effect generated by the force about a certain axis, it is proportional to three things. Firstly, it is proportional to the size of the force. Secondly, it is proportional to the distance from axis of rotation to where the force is applied, so the distance r. Finally, it is related to the angle between the force and the r vector, the angle phi at here. If the angle phi is 0, that means the force is parallel to the r vector, either 0 or 180 degrees. So F is parallel or anti-parallel to the r vector, it would not contribute to the turning effect. Turning effect is greatest when phi is equal to 90 degrees. So we could see that it is the component of the force, F sine phi, that is most important. Component of the force parallel to R contributes nothing. So that is why we have the sine phi in the equation. At here, you will see the torque, which is the measurement of the contribution to turning effect. It is proportional to R, F, and sine phi. And in the vector operation, we give it a certain name for this type of a calculation. We call this the vector product. So this type of a calculation is a vector product. Or sometimes we call it the cross product. Because as you can see in the notation, the torque, it is written as R vector cross F vector. It is written with a cross in between the two vectors. Remember, there was another type of a vector operation, and that is the dot product. You saw the dot product or the scalar product. I type it in another color, scalar or dot product. You saw it in the case of a calculating work done. Work done is equal to F dot R. In the case of a dot product, it is equal to F times R times cosine theta. The outcome of the dot product, it is a scalar quantity. Work done is a scalar quantity. On the other hand, the torque, it is a vector quantity because if you apply the force in different directions, the torque generated would be in different directions. So torque is a vector quantity. And the idea is you are having this cross product, which is equal to R cross F. Numerically, it is equal to R times F times sine phi. Phi is the included angle between the R vector and the F vector. And you could actually group the R sine phi together. So R sine phi, as you will see, it is equal to D, the perpendicular distance between the force vector and the axis of rotation. At the same time, you could also consider the grouping of the force F and sine phi, which means the component of the force perpendicular to the R vector. In any case, we are only considering the components of the R vector and the F vector that are perpendicular to one another. So that is a very important concept. The component of the force and R parallel to one another, they do not contribute to any turning effect. Only the components of F and R that are perpendicular to one another, they contribute to the turning effect. Here, D is R times sine phi, and in terms of mathematics, it is the perpendicular distance between the axis of rotation and the force vector direction. In the physics, it is also regarded as the moment arm of the force. So this moment arm of the force, in terms of mass, it is just the perpendicular distance of this line from the axis of rotation. Now, a vector carries direction. So here, the direction of the vector, strictly speaking, is determined by the right-hand rule. But we are not trying to make the things complicated here. We try to only look at the things in the two-dimensional case. So if you have a force that would generate a turning effect in the anti-clockwise sense, let us take it as a positive torque. If a force that generates a turning effect in the anti-clockwise sense, we call it a positive torque. If it is generating a rotation in the anti-clockwise sense, it is called a negative torque, if you like. So that would make the things a little bit simpler rather than considering the actual vector directions, because if you consider the actual vector directions, things would become quite tricky for understanding in this level. So we just consider clockwise torque and anti-clockwise torque. Say at here, you have not one single force, but a number of forces. So each of the force, due to the separation of the force from the axis of rotation, it would be responsible for a certain torque. So each of the force will be generating a torque, some of them contributing to an anti-clockwise torque. Say here, this one would be contributing to the anti-clockwise torque. Otherwise, say in the case of an F2, it would be generating to a clockwise torque. The net torque, it is equal to the sum of the clockwise torque and the anti-clockwise torque. Now, once again, to make the calculations more straightforward, let us consider a torque generating rotation in the anti-clockwise sense to be a positive torque. So F1 times D1, it is a positive torque because it generates rotation in the anti-clockwise sense. The torque F2 times D2 generates rotation in the clockwise sense, and that is a negative torque. So that is why we have a minus F2 times D2. Although when we write it down, it can be written as plus torque 2, because if it is a vector, strictly speaking, you are correct. But in terms of a magnitude, the net torque has to be added by considering whether it's a positive torque or negative torque. So let's take a look at an example to justify our discussion. This is a complex cylinder. You have two parts of a cylinder, and they are having different axis, different radius of from the axis of rotation. Rotation axis is a Z axis. So there are two strings or two ropes wrapping around the two cylinders. One is applying a tension T1 along the positive X direction. The other one is the T2 applying along the negative Y direction. So in the first part, we ask what is the net torque acting on the cylinder about the axis of rotation, which is the Z axis. The net torque can be considered in this particular case by observing the turning effect about the Z axis, for example. So you have the rotation due to the tension 1 that is in the clockwise sense. When you wheel along the negative Z direction, so we are wheeling from this side into the paper, if you like. So the torque T1 would be generating a clockwise torque. And this would be, according to our convention, a negative torque. So you have minus R1 times T1. We are not assigning the positive or negative according to the cross product, but according to our observation at here. So T1 is generating a rotation in a clockwise sense when we wheel along the negative Z direction. So when we wheel on the XY plane, it is generating a clockwise rotation, so minus R1 T1. On the other hand, the tension T2, it is causing a anti-clockwise rotation, so R2 times T2. The net torque would be the sum of the torques, so R2 T2 minus R1 T1, because they are generating rotations in different senses. So you have a minus sign for R1 T1. And then in the part B, suppose T1, well, we give it numbers, T1 5 Newton, R1 1 meter, T2 50 Newton, and then R2 0.5 meters. So net torque in this case can be calculated. The torque, which is equal to force times distance, would have a unit of Newton times meter. Newton times meter. So the net torque is R2 T2 minus R1 T1 in this example. So this is 2.5 Newton meter. It is a positive number. So in the XY plane, it generates the anti-clockwise rotation. So a negative value refers to the anti-clockwise rotation in this case. Positive, well, sorry, a positive value means anti-clockwise rotation. Negative value means clockwise rotation. Okay. And we could now take a look in the relation between the torque and the angular acceleration. So the idea would be pretty much like the Newton's second law. In the Newton's second law, it states that when there is a net force, it would lead to an acceleration, a linear acceleration of the object in the direction of the force. So similarly, in the case of a rotational motion, a net torque would have an effect of generating angular acceleration in the same sense as the torque. So in the same direction as the torque, if you like. So here, it starts by considering the linear motion and then try to generalize it into the rotational motion. Here we start with a particle. The particle is making a rotational motion, but instantaneously it would have a linear velocity. If the particle is accelerating along its tangential direction, there must be an associated force. Newton's second law. Force equals to mass times acceleration, and it would be the tangential force that causes the tangential acceleration. Of course, because the particle is revolving, it is rotating in a circular sense, it would also be experiencing a centripetal force. But this centripetal force, it would not contribute to the torque because the centripetal force points towards the axis of rotation. So R times F times sine phi would be equal to 0 because the force is parallel or anti-parallel to the distance. Phi is equal to 180 degrees. So this radial force would not contribute to the torque. Only the tangential force would contribute to the torque. So this tangential force multiplied by the radius, it is the torque. The net torque, it is equal to the tangential force times the radius. And this tangential force, according to the Newton's second law for linear motion, m times a. A is the tangential acceleration. Tangential acceleration, it is equal to r times alpha. Very important, this is not centripetal acceleration. Centripetal acceleration, if you go back to the circular motion, centripetal acceleration, it is equal to v squared divided by r. And here, or it is equal to the omega square r. Because the tangential velocity is related to the angular velocity by v equals to omega r. So centripetal acceleration is given by this one. Tangential acceleration along the tangent direction, at, it is equal to alpha times r. At equals to r times alpha. So you could rewrite the equation mr alpha times r. mr times r becomes mr squared, which for a single particle, it would just be the moment of inertia for that particle about the axis of rotation. So for this particle, it has a moment of inertia I about the axis of rotation, and the effect of torque, as you will see, is to generate a angular acceleration. And the amount of angular acceleration depends on the inertia of the particle to rotate about a certain axis. If you have a collection of particles, it depends, it would be the moment of inertia for the whole object. So here you see the equivalent of the Newton's second law in the rotational form. The impact of the torque, the net torque, is to generate an angular acceleration, and the proportionality constant, it is I. So I is, once again, the inertia of the object to rotate about a certain axis. So you could find out once again the similarity between the linear motion, which in the case of a linear motion, the equation is F equals to ma. You could find a similarity between a linear motion and rotational motion. F equals to ma. Torque equals to I alpha. Of course, here the torque is the net torque. Now let's take a look in another example and see the effect of the torque. The rod at here, it is hinged at the end, so you have a pivot, and it is now undergoing free fall. Well, not really a free fall, because if you have a free fall, it is free from influence of anything. Here, it is not free fall because it is under the influence of the pivot. It cannot fall as a free object, but it has to rotate. So what would be the corresponding motion of the rod? And in particular, what is the corresponding motion of various points of the rod? Say at here, you have the rod that is uniform in mass, so we could assume all the weight. You could assume all the weights to be focused at the center of mass. So mg is at the center of mass or center of weight, if you like, but they are equivalent in the practical sense. Now, when you allow the rod to be released, it would have a torque. It would have a torque about the pivot. So the torque, of course, if you look at it in this direction, you would say the torque is in the clockwise sense, but it doesn't really matter. Let us just consider there is a torque. What is the magnitude of the torque? It is equal to the force mg times the distance, L divided by 2. So the net torque, there's only one torque due to the weight, mg times L over 2. And it would cause an angular acceleration about this point by the Newton's second law in the rotational form. The net torque over I. What is I in this case? Rotation is about the end of the rod. So from the previous slide, it is equal to ml squared divided by 3. No need to remember this equation. They would be provided, if necessary, in the examination. So net torque divided by moment of inertia, and that is 3g over 2L. This is the angular acceleration. So for every point on this rod, it is a rigid rod. For every point on this rod, it would have this value of angular acceleration. Let us consider a specific point on the rod, say the end of this rod. What is the tangential acceleration at the end of this rod? If you have a rod that is a rigid one, the angular acceleration about this point, it is equal to 3g over 2L. Length of the rod is L. So tangential acceleration the tangential acceleration, it is equal to L times alpha. It is equal to the length, the distance from the axis of rotation times the angular acceleration. So you multiply it by L, it becomes 3g over 2. Now, that is funny. Acceleration at the end of the rod, it is even greater than the acceleration due to gravity. So if you have any object placed at the end of the rod, say a cone, and you release the rod from rest, the rod would be accelerating faster than the cone when you release the rod. This means that the cone will be detached from the end of the rod because the rod is accelerating quicker than g at the end of the rod. So this is an observation we could get from the calculation. Some of the classmates is asking, is the I inertia of the center of mass? No, this is the I is the inertia about the end. The center of mass of this rod must be at the center if it is a uniform rod. So if your rod is rotating about its middle, the center of mass, it is ICM. If it is rotating at the end, most likely it is not ICM. So that is why we have the 1/3 ml squared it here. And this is a picture that shows you the collapsing of a chimney during the destruction, not the construction, of a factory building or a power plant. And here you will notice one very striking thing. The chimney is broken at some point in the middle. Remember, when the chimney is falling down, it is kind of like the previous example. You have the chimney that is falling, so you have to use a bit of imagination, rotating the whole picture by 90 degrees. So the chimney is falling down. At some point, the acceleration is even greater than the weight of the the acceleration is even quicker than the acceleration due to gravity. So it would be the very large force greater than the weight of the object. So this shearing force can sometimes greater than the strength of the chimney, and it would cause it to break down in the middle of the rod. So that is just one example. I just put a example 10.10 at here, and let me try to take a look at the question. Why AT doesn't have to be divided by L? If you go back to the example 10.8, A is the tangential acceleration. It is a linear acceleration. It is related to the angular acceleration by A equals to R times alpha. So that would be on page, let me see, that would be on page 17 on your lecture notes. Tangential acceleration, it is equal to the angular acceleration times the distance, not divided by it. Right, at here you have a angular acceleration because of the angular acceleration of a wheel due to a falling object connected by a string. So at here we have two types of motions connected together by a string. So parameters are basically given on the diagram. The mass of the wheel is m, moment of inertia is large I, and the mass of the block is small m. So you're asked to calculate the angular acceleration of the wheel, the translational acceleration of the object, and the tension in the string. Let us try to understand the whole thing. Basically, you have three you have two objects at here. You have a disc or the wheel, and it would be rotating, in this case, in the clockwise sense, if you look at it along this direction. So why is it rotating? It is because you have a string attached to it, and the string is giving attention. So it would be receiving a torque due to the tension in the string. And at the same time, you have a block that is pulled upward by the tension and pulled downward by the weight. So if the string is not extensible, if the string is not elastic, that means the tangential acceleration of the wheel has to be equal to the downward acceleration of the block. That is a very important hint at here. Rotation acceleration is alpha for the wheel. So we could write down several equations at here. First, it is the Newton's, well, first we consider the wheel. There is a torque, a net torque acting on the wheel due to the tension in the string. Of course, the wheel has a weight, but the weight is at the center of, the weight is at the axis of rotation, and it would not contribute to the torque. So only the tension in the string contribute to the torque. And that is equal to I times alpha. Alpha is the angular acceleration. So alpha is equal to torque, tension times the radius of the wheel divided by I. And for the block, it would be the difference between the weight and the tension that give rise to the net force for the acceleration. So acceleration equals to mg minus t over m. Nothing difficult here. Important part, the most important equation in the question would be this one. A equals to R times alpha. Because the tangential acceleration is related to the angular acceleration by this equation. So with that, you could replace R times alpha equals to TR squared over I. And in that case, you could find out what is T in terms of M, R, and I. And then you could find out what is A once you got the T. Once you got the T, you could find out the A as well as the alpha. So we have to separate the whole problem into different parts when we do the calculation. And by means of a suitable connections between the rotational motion and the linear motion, we could have these additional equations to solve the problem. Okay. Before we move on, let us take a look at another tutorial question. And I will show the question. And that is question number 4. Diagram of question number 4, it is the right-hand side diagram. And this question number 4 would see. It will be kind of related also to question number, example number 10.12. But here we just take a look at question number 4. So you have this diagram. Basically, it is a pulley in the linear motion. You will have seen this diagram before, but in those cases, you have pulleys that have no friction on the surface. So the string would be having equal tensions on both sides. Here, the strings do not slip on the pulley. So that means there are some frictional force on the pulley. It is very difficult if you really consider the frictional force. On the other hand, they are internal forces, so they should balance on the two sides. At the same time, we could instead consider that there are different tensions in the string. Why we need different tensions in the string? Because if you have a pulley that has a certain mass, if we want it to be rotated, if we want the pulley to be rotated, then there must be a torque. So why does the pulley rotate? If it has a moment of inertia, if the pulley has a moment of inertia, why would it rotate? It rotates because there is a net torque. According to the Newton's second law. So the net torque must be arising from the tensions in the string. So they are different tensions, T1 and T2. The tension on the mass 1, the tension on string on the mass 1, let us call it T1. Tensions on the string in mass 2, let us call it T2. So the difference of tensions in the string, it is the reason for the net torque acting on the pulley. So at here, we could try to find out what is the acceleration of the pulley, alpha, what is the angular acceleration of the pulley. And if the string do not slip, then the angular acceleration of the pulley is related to the tangential accelerations of the mass by A equals to R times alpha. So that is the idea of the problem. So let us take a look at the solution here. Right. So we have, as I've said, different tensions in the strings, T1 and T2. T1 is the tension in the string on the mass M1, and T2 is the tension in the string on the mass M2. So you could see that at first we try to write down all the equations. What are the net forces acting on M1? It is responsible for the is responsible for the linear accelerations for the mass m1 and mass m2. And due to the difference in the tension, we could see that there is a net torque. Once again, here we write down the torque. It is giving it a different sense of rotation. So the alpha may be of an opposite sign, but it doesn't matter as long as we figure out the correct senses. So here, T1 times R1, it is giving rise to, okay, actually it's a right sense of rotation. T1 times R1 causing the anti-clockwise torque. T1 times R1, so it's positive. T2 times R2, on the other hand, it is giving the clockwise torque, so it's a negative value. The difference of the torque, it is equal to I times alpha. This is a wheel. Axis of rotation is here, so it goes all the way downward. According to the table for the moment of inertia, for such a wheel, use a bit of imagination. This is the wheel. Of course, you will say this is a cylinder, but if your cylinder is getting thinner and thinner, then it becomes a wheel. So the moment of inertia, it is about the center of mass, and it goes all the way through the axis. So it is 1/2 mr squared. So that is why you have here 1/2 mr squared as the moment of inertia for the wheel times A divided by R. So A is the tangential acceleration and R is the radius of the wheel. So A divided by R corresponding to the angular acceleration. So with that, we have a total of 3 equations, and we would be able to solve for the value of A, the linear acceleration. With the linear acceleration for the masses, we could find out what is the time taken for the block M1 to drop onto the ground. So that is the idea of this question. And in the part B of the question, it is asking, what if the pulley is massless? If the pulley is massless, then, as you will see, basically this term would be cancelled, and this would increase the acceleration of the blocks. So the torque is not being used to generate the angular acceleration of the pulley, and this would save some force, if you like, to accelerate the blocks. So that is the idea of this question number 4 in the tutorial. Now, let's try to quickly go through the last topic I would like to discuss about, and that is the concept of the work done. The idea of the work done in the case of a rotational motion, it is once again very, very similar to the case of the work done in the linear motion. Of course, we have seen this equation. Rotational motion have the kinetic energy that is equal to 1/2 I omega squared. And how does the kinetic energy come from? Where does the kinetic energy come from for the rotational motion? there must be an external torque moving over a certain angular distance. Remember, in the case of the linear motion, where comes the kinetic energy in linear motion? It is still the work done. Force moving over a distance is the work done. So if you have an object experiencing a force and causing the center of mass to displace by a distance, it would generate a work done. Here, a small work done is generated by having the force applying to the object, causing it to move a distance ds. This force and distance could be resolved such that the force parallel to the displacement is useful for the work done. What is that force? It is F times sine phi. Phi is the angle between the r vector and the f vector. Phi is the angle between the r vector and the f vector. If you cannot remember this definition, go back to the page of the torque, the definition of torque. So this torque, this force, parallel force, parallel to the displacement ds, it is F times sine phi times ds. ds is r times d theta. ds here, it is equal to r times d theta. And at the same time, the force parallel to displacement, it is F sine phi. Grouping them together, F r sine phi, it is equal to torque. And d theta remains. Once again, we find similarity between the linear motion and the rotational motion. Work done in a linear case, force times displacement. In the angular or rotational motion is torque times angular displacement. So you see the connections between the two. So with that, we could rewrite I times alpha for the torque times d theta. And here it is just another way to derive the equation for the kinetic energy or work done in the rotational sense. So the relation between the work done and the kinetic energy can be shown by this calculation. When you have a work done, you are converting, when you have a work done on the rotating object, you are converting it into the rotational kinetic energy. Okay. So here we have a number of equations obtained for the rotational motion, and they could be always compared with the linear motion. So here is just a summary of various equations. We have covered most of them, except a few important, with a few important exceptions, and that is the ones that are at here, basically. Sorry. We have not talked about these two, linear and angular momentum. They are related to one another as well. Most of the ones above, they could be, they have been covered, and they could be used interchangeably in the equation form. Of course, we have to be careful that when we are talking about this, we are actually working on rotational motion. Right. We would take a look at here two examples before we conclude this lesson. The first one is the connection between the rotational kinetic energy and the gravitational potential energy. You have this rod. Now here it is rotating under the influence of the gravity. So you could calculate what is the conversion between the gravitational potential energy and the rotational kinetic energy. The gravitational potential energy, it is equal to 1/2 mgl. The center of mass is in the middle of the rod. Remember, very careful. Be very careful. Center of mass is at here. After the rotation, it just falls by L/2. So the change in the gravitational potential energy, 1/2 mgl. Kinetic energy, on the other hand, is a rotational kinetic energy, 1/2 I omega square. I is moment of inertia about the end of the rod, so it is equal to 1/3 ml square. So that is why you have the angular velocity that is equal to 3g/L square root. The linear velocity, it would be, of course, in this direction when it is falling at the bottom of the motion, and that is equal to square root 3gl at the end of the rod, and it is equal to 1/2 square root 3gl at the center of mass. So that is interconversion between the gravitational potential energy and the rotational kinetic energy. And this is an example similar to the question number 4 in the tutorial set number 3. But here we are trying to calculate the speed of the particles. And at here, you have the mass m1 rising by a distance h, and at the same time, m2 is dropping by the same distance in the other direction. So the change in the kinetic energy, change in the gravitational potential energy, it is m1 gh minus m2 gh. And the loss in the gravitational potential energy is converted into the gain of the kinetic energies of the masses as well as the flywheel. Flywheel has the I that is equal to, well, it is not specified, but it is the kinetic energy 1/2 I omega f squared. Connection between omega f and the Vf can be obtained through the equation Vf over R equals to omega. So that is the equation we have seen before. V is equal to omega times R. So in this way, we could connect the velocities of the particles and the angular velocity of the flywheel. So that is how we could use the conservation of energy to calculate the problem. Okay, right. I would have to stop at here because the rolling motion would be something quite difficult, and I would need some time to discuss it in the next lesson. So I would end the lesson at here. Remember that if you have checked on the Blackboard or Learn at PolyU, some assignments have been given to you. So there's assignment 1.3 and 1.4. The due date is 5th of October, and that would be the coming Monday. So you still have some time to work on it. Altogether, there are 7 questions for the 2 assignments. So that is not a lot. There are altogether 7 questions. So that should be okay. Right. Once again, thank you very much for attending the lesson on this Saturday afternoon. And the video would be posted on Learn at PolyU later today. So I will stop the lesson at here. Thank you very much.